Hi, folks. Time to talk about assignment three. Assignment three has a lot of problems, and I'm looking at the fact that it's going to probably be, if I worked out every one of them, 28 problems start to finish, I think it would take a long, long time. And therefore, I'm not going to work them all out. I'm going to talk through some of them because I feel like I've shown you what you need to do to prove convergence or divergence enough on the previous two assignments. So instead, I'm going to give you like a shorthand version of the solutions. But please note that if you were doing this on a test, if you're doing this on the AP exam, you do need to do the complete solution like we did previously in the previous problems, the previous assignments. So what we're going to start off with is number one, and I'm going to kind of give you the really quick shorthand why, but I want you to see that, 1A, I want you to notice is a simple p-test, right? It's a p-test where the p equals 3, which is greater than 1, and therefore it converges absolutely. If you took out that negative 1, right, because really what that is, right, I mean, I want you to see that this is just rewritten, right? I'm just rewriting this problem. Right? That's all that problem is, folks. And I need you to recognize that this is just literally this. It's not even alternating. It's just the negative of something that we talked about before by the p-test that converges, right? 1b, let's look at this. I mean, you kind of start writing out some of these terms. Let's put in 1. What do we get? We put in 1. Oh, I think we get 0. And then plug in 2. Negative 1 over 4. Let's plug in 3. Negative 2 over 9. One more? Okay, let's plug in 4. Folks, that's not even alternating, right? It's not even alternating. So we know it's not alternating. It's not. It doesn't have a chance. But okay, so this assignment 3 says alternating series. Why are we even worrying about it? Well, we're not even worrying about it because we're kind of thinking about absolute convergence first, right? We're thinking about absolute convergence. And if I look at 1 minus n over n squared, what I see pretty quickly, folks, is this is just kind of 1 over n, right? It's kind of 1 over n, right? Just like 1 over n. And that limit is going to be some negative 1, which is a non-zero constant. And that non-zero constant means they're going to diverge together. The bottom diverges, so the top one diverges too. Again, shorthand version. Okay, now we have an alternating series. That's awesome, right? That cosine of n pi is something we've seen before. And then when you go from 1 to 2 to 3 to 4 to 5, it's just changing signs, right? So it can be rewritten like this. You have to recognize that cosine of pi, then cosine of 2 pi, then cosine of 3 pi, then cosine of 4 pi is just alternating negative ones. But again, the fact that it's alternating is irrelevant because this guy right here would have converged already, right? This converges by the p-test. So it converges absolutely. The fact that it's alternating doesn't even make a difference. Well, D, folks, I mean, this isn't even an alternating. It's not alternating at all. I mean, this is just this. But again, we're not talking about whether it's alternating or not. We're just talking about does it converge? Well, yeah, this converges absolutely because you just compare to, you just do a comparison test. I'm doing a lot of limit comparison tests here. But yeah, limit comparison tests, they converge together. Again, if what I want you to be thinking about is if you just did the absolute value of this, if you forgot about the negative, right? When you're doing you're testing for absolute convergence. You're forgetting about any of the signs. You're just saying, look at the absolute value of the terms. Does the absolute value of the terms, that's just the positive version of it. Does that converge? If it does, then it converges absolute value. I mean, absolutely. Okay. 1e. I guess I'll take a second just to rewrite this, right? I'll just rewrite it for you. Because you can take the negative 1 out, and the negative 1, doesn't make a difference for whether it's in the numerator or denominator. Right? So what is this, folks? Yep. And what happens with r equals 1/5? Well, it's less than 1, and therefore it converges absolutely. When you're doing this, you're literally saying, when I'm testing for convergence absolutely, you're literally saying, forget about that. Does that converge or not? That's all you're asking the question, okay? Houston, we have a problem. I say that because this puppy is not going to converge. Absolutely. In fact, if I compare this, limit comparison test again, I'm going to get 1/2, which means these two are going to diverge. So if I did the absolute value, if I took all the positive terms, right, the absolute value series, right, the absolute value diverges. So what does that mean? Well, if the absolute value series diverges, we know it does not converge absolutely. Absolutely. But it could converge conditionally. To test that, what do we have to do? Okay, we have to look at this. Is it alternating? Yes. Is this getting smaller and smaller? Well, yeah. Plug in, 1, then 2, then 3, then 4, then 5. The denominator is always getting smaller. So consistently, a of n plus 1 is smaller than a of n. And yeah, that's clear as day, right? You plug in infinity here, you're going to get 0. So we have all 3 requirements for conditional convergence. So 1f is our first example. Yay! We found one that doesn't converge absolutely, but does converge conditionally. Well, that one doesn't even have a chance, does it? Right? Right? I mean, this doesn't really make a difference, whatever the number that is, because the limit as n approaches infinity of n over n plus 1 does not equal 0. It's equaling 1, right? This equals 1. So therefore, this doesn't meet, this first of all fails the original very first test that we did, the divergence test. It diverges, if it was not alternating. But it also fails number 3 in our checking of our convergence. It fails this guy that we just did right here, right? It fails that. So it fails this condition, meaning it diverges. And folks, same thing for h, right? 1h also diverges. I mean, it's the same thing, right? It's actually, sorry, it's -1, right? You plug in infinity, you get 1 over infinity minus 1. So instead of being +1, the limit equals -1, which also. Okay, so that's number one. And number one was kind of the kind of beginning, our segue into the stuff. And hopefully it's making sense to you. We will need to make sure that when we're going through these processes, we're kind of first looking for absolute convergence. And then after we find absolute convergence, if we don't find absolute convergence, we then decide, does it diverge or does it conditionally converge? Number two. Again, I'm going to be a little bit quick with the absolute convergence. So the first thing I'm going to look at is this. Did I put that right? Yeah, I guess I made that too big, didn't I? Okay. So this is the absolute version, right? This is the version of it. This is the non-alternating version. And I want you to quickly see that you have kind of n to the 1/2 over n. N to the 1/2 over n shouldn't feel good. Should not feel like you're going to actually converge. It should feel like you're going to diverge. And then all you have to do is come in and do a limit comparison test. If you're saying, wow, we're doing a whole lot of limit comparison tests, yeah, you're right, we are. And you do a lot of limit comparison tests on these type of problems. So, okay, this is going to equal 1, which is a non-zero constant. Meaning that this series here diverges. So therefore, this series, the question that we're asked, I mean, this is the big kind of difference. The one we're asked about, which is this problem, this is the alternating version. So because this guy up here diverges, we know that this guy, that's alternating version, he just doesn't converge absolutely. That's all we know. So now we have to determine conditional convergence or divergence. Is it alternating? Yes, it's alternating. You see it right here. 2. Is it getting smaller and smaller every term? Well, that gets a little bit trickier for us to see because one of the things that it's harder for us to visualize, at least, is what's happening as n gets larger. Sometimes it's easier for us to kind of manipulate this. If we think about this, it might be easy to kind of multiply top and bottom by 1 over root n. And if we do that, we're going to see this. For some of us, this makes it easy for us to see that as n is getting larger and larger and larger, we can see in this kind of fraction here that as n is getting larger, that this is, each term is getting smaller and smaller, right? Just think about it, right? As n is getting larger, the denominator is going to be is going to still get really, 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 really big, but the numerator is just going to get closer and closer and closer to 1. So the numerator is not getting really any bigger. The denominator is getting larger. So therefore, as n gets really, really, really big, the a of n plus 1 is getting smaller and smaller relative to a sub n. And lastly, we have this. And that's true if you look at the same thing that we just talked about, right? So sure enough, we have all conditions are met. We have conditional convergence. That was fun. So again, what do we do first? We check absolute. And when we look at absolute, the first thing we look at is just say, hey, forget about the negatives. Pretend they're all positive. Are our instincts there yet, folks? Do we have them yet? N over n cubed. What's it going to look like? Yeah. So by the limit comparison test, this converges. Absolutely. Right? Again, we'd have to write a whole lot more out if it was on a test. Oh, this one looks tricky. Well, why is it tricky? Well, first of all, I mean, it's clear as day. To me, at least, clear as day. Not going to condition, not going to converge absolutely. Right, because what is this doing, right? Well, hold on. This actually, the limit equals 1. So not only does this, diverge by the divergence test, but it also doesn't meet requirement 3 of conditional convergence, right? It's not equal to 0. So it's definitely going to diverge. And that's like a quick giveaway, folks. If you ever see a term that isn't approaching 0, if you ever see a sequence that is, as n gets big, is not approaching 0, it's definitely going to diverge, because the divergence test tells you that if it was all positive, it's going to diverge. And the alternate series test, the one that says check these 3 conditions, the third condition says that it has to equal 0 as well. So we have automatic diverge there. That's a key giveaway. 2D. Well, that kind of looks fun. I mean, I really love this stuff. I mean, actually, I'm not going to use that yet, right? Well, maybe I should, because I saw what's going on. I'll leave it in there. I love this stuff. I love when I look at a problem, and at first it looks like it's crazy hard, and then you use one little trick, and then like it's suddenly super, super easy. This is what makes math fun. So you see, you have this. If I showed this to some other folks, they'd be like, what the heck am I supposed to do with that, right? I mean, how the heck am I going to start thinking about that? And all you really need to do is use your laws of logarithms. Oh, wow. Yes, folks. This series is literally adding a half, then subtracting a half, and adding a half, and subtracting a half. That's literally what's going on there. And because it doesn't equal 0, it diverges. Yeah, those are fun. Well, I mean, I got an instinct, right? My instinct is ln of n gets to infinity way too slow. It's going to diverge, right? That's my instinct. So my instinct is right away that this does not converge absolutely. We do need to prove that it's not going to, absolutely converge. So we have to check this first. So we have to check this first, right? We have to check to see if this conditionally converges. Because my instinct is to think right away, ln of n slower than n, I think I'd just use the comparison test. I mean, my idea would be this guy here, ln of n is usually quite small. So therefore, this is going to be greater than 1 over n. And when does that happen? Well, it really starts from the very beginning. The ln of 2, the ln of 3, the ln of 4 is always, ln of 3 is always smaller than 3. ln of 4 is smaller than 4. So I'm going to use that comparison test. And this is true for all n greater than 2. Why do I care about 2? Because that's the number right here. So this is true. And therefore, because this converges, this diverges, and this guy's always bigger than that, he diverges too. So we know, now, so we know the absolute value diverges. Boom, we know we can come over here and say it can't conditionally converge, right? This diverging means can't. Sorry, I said it wrong. Can't absolutely converge. It can conditionally converge. So let's check. Does it conditionally converge? 1, it's alternating. Dead giveaway right here, right? That's a huge giveaway. 2, is it getting smaller and smaller? Well, yeah, because it will ln of 2, then ln of 3, then ln of 4, then ln of 4. Each denominator is getting slightly bigger, so therefore each term is slightly smaller. It's getting bigger in the denominator, just taking a long time. It goes really slow. And if you take this out to infinity, it does indeed equal 0. Therefore, we have conditional convergence. Yay. 2f. Where are you, 2f? Oh, there you are. Finally, we don't have to use, we aren't able to use our limit comparison test. Finally. I have to say, is this whole assignment limit comparison test? So let's test this first, right? Again, test this first. Test for absolute convergence first. And I'm doing that for a reason. When I see n cubed over something factorial, I know the factorial gets huge really fast. So when I see the denominators getting huge really, really fast and the numerators relatively slow, I'm pretty confident that this is going to converge. But let's use the ratio test. Just so we can kind of make sure we can still know how to do this. I know that we did this last assignment, but let's just make sure we can still do this, right? Ooh, n plus 2 factorial. All right. Again, I'm going to use my technique of splitting this up. Multiply by the reciprocal. I'm going to put the n plus 1 factorial here. I'm going to put the n cubed here. Why? Because this makes it nice and clean for me. I see that this is going to basically simplify to 1 times 1 over n plus 2, which is 0. And if rho is 0 and is less than 1, we have convergence. And because we took the absolute value of this, and we see that the absolute value of the terms converge, we have absolute convergence. We didn't even have to check the negatives. They were completely irrelevant in that problem. This next one. I think this also looks like some sort of ratio test. See, when I have exponentials, that's what I kind of go to. When I have exponentials and factorials, I kind of go there first. Okay, so let's test if this is going to converge absolutely first. So again, I'm forgetting about the negative for a second. I'm just testing absolute, right? Testing for absolute convergence first. I'm hoping that you can follow me. Folks, I'm going to do a few steps together at once. I hope you can follow me. If you don't see this, do what I did up here. Okay, do what I do up here. If you can't see that ratio, how I did that, but basically I kind of jumped to here, kind of, right? So this is rho, and rho is less than 1. Therefore, we have convergence by the ratio test. And because we did the absolute value of it, we have absolute convergence. We don't even have to test the negatives. You might be saying, Mr. Poprick, 2f and 2g, you just acted like the negative wasn't there. Well, yeah, you're right. I did. I acted like the negative wasn't there to start. Because if the negative isn't there and we have convergence, we're done. We have absolute convergence. It's only if I get rid of the negatives and then after that I notice we don't have convergence, then we have more work to do. So in both those examples, we kind of took a shortcut. We just didn't need to worry about it anymore. So we're going to keep going. We're on a roll, right? Ooh. So this is going to be a little bit odd, right? This is definitely a little bit odd. So the reason why it's a little bit odd is because you have this 1 over n and L of n. I mean, it's a little bit faster than 1 over n, right? 1 over n kind of was that threshold, so I'm not so sure if it's going to converge or diverge or not. Luckily, we have a couple things that we can do to kind of start thinking about this. So to start thinking about the absolute one first. Let's look at this. Because if this converges, we have absolute convergence, we can go on to the next problem. How are we going to look at that? Well, you know, I might see this a little bit different than other people, but when I look at this, I feel like this is an integral test. The reason why is I see that if this was my u, that would my du. So I'm going to kind of say, hey, let's treat this like it's an integral. And we know that these two are going to converge and diverge together. So now if I think about this, I'm going to turn it into a limit problem. And when I look at this integral, I like it because if I make u equal to ln of x, my du is 1 over x dx. So therefore, this effect of this integral is going to turn into 1 over u, and then u to the negative 1. If I do the integral of u to the negative 1, I get the ln of u. Oops, no integral anymore. Right, so it's going to be the ln of u plus c. So this beautiful integral right here, really when we figure out, it's going to be the ln of u, which is the ln of x. So it's going to look like this. Oh, I forgot a b up there. I'm sorry, folks. Whoops. That's better. ln of infinity. Well, that's getting to infinity really slow. We talked about how ln of infinity is slow. The ln of infinity is ultra slow. I mean, it doesn't get much slower than that unless you did like the ln of 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 infinity. I guess that's even slower. But this is diverging very slowly. Darn it. Guess what that means? We don't have absolute convergence, right? Diverging slowly means no absolute convergence. So we have to come back and test. Do we have alternating? Yeah, we have alternating. I mean, as long as this negative 1 is to some kind of regular power n or n plus 1 or n minus 2 or n plus 15, as long as it's not like a 2n or a 3n here, it's definitely alternating, right? 2. Is this getting bigger? Well, look what happens when n gets larger. As n increases, this is just going to keep on getting bigger. If the denominator gets bigger, the fraction gets smaller. So it's getting smaller every turn. And sure enough, that's 0, clear as day. Check, check, check. Conditional convergence. So the heavy lifting, right, folks? The heavy lifting is when we do the absolute conversions. That's the harder work. That's the harder kind of. We had to use the integral test here to figure that out. That's why we start with that. Some people would say, well, Mr. Poprack, it's so easy to check for conditional convergence. Why don't you do that first? Once you get conditional convergence, you still have more work to do. So you might as well do the heavy lifting first. I'm just going to rewrite this just so we see what we have to think about. Haven't seen something like this before. So we're going to figure out a way to do this. If we take the negative one out, really the thing that we have to check for absolute convergence is this guy on the left, right? So let's start thinking about how we're going to tackle this. I don't have a quick instinct except for to say that my feeling is when I'm looking at this stuff, ratio test is probably going to be useful. I mean, whenever I have exponentials, it's kind of my go-to. So the problem is, I mean, this is where we're going to be really happy that we did some work earlier this year when we did limits. And this is going to, it's going to be a little messy. This part's kind of clean. This part, not so much. So this part here, I mean, there's a reason we did this earlier this year, folks. I want us to be clear that this part is clearly 2, right? Somewhere. And the way that we solved these earlier this year is that when we had something like all these different terms going on, we divided each term by 5 to the n. We multiplied top and bottom by 1 over 5 to the n. Now, what's n over 5 to the n? Well, if you look at that as that goes to infinity, the exponential is much faster. So this is going to be 0, this is going to be 0, this is going to be 0, this is going to be 1, and this is going to be 5. So we're going to get 1/5. So that's why this whole answer is going to be 2/5, which is our row, and our row is less than 1. And therefore we have convergence by the ratio test. The ratio test here is telling us that a row is 2/5, which is less than 1. And because we did the absolute value of it, we don't have to worry about the conditional stuff. We have absolutely convergence. Absolute convergence. I don't think I need the ly, do I? Absolute convergence. Are we done the last problem already? Darn it. The good news is we didn't leave something easy for last. Can I do that, folks? You all right with that? Okay. So, I mean, writing it that way works for me, especially to think about it when I'm looking at this and saying, yeah, that's how I'm going to be thinking about the terms. But when I'm thinking about this, absolutely, I might want to just write it this way for a second. And I want you to kind of start thinking about this. There are times where it just kind of helps to think about your instincts. And we could go through a limit comparison test. I mean, let me take you back. If you want to see how to do this with a limit comparison test, go back to assignment 2, number, let's see, I found it somewhere, 1J, and sorry, 1I. Go to look at what I did for 1I. You can see that we could prove this another way. But for this one, there's a cleaner way, and it's kind of more similar to what we did way back on assignment 1. Wow, we're a little way back. Assignment 1, 1C. And we can use that skill of look what we did on 1C on assignment 1 to kind of think what's happening here. Let's think of what's happening. Okay, let's plug in 1. What do we get? Plug in 2. Plug in 3. Plug in 4. Plug in, and we keep on going, right? That's what the sequence is going to do. Eventually, you're going to get to some huge number, right? This big number, a gazillion. And you have just subtracted some bigger number, some number right before it. But all the numbers are canceling out. Like ln of 1 is 0, right? This is 0. But ln of 2, cancel with that ln of 2. This ln of 3, cancel with this ln of 3. This ln of 4, cancel with this ln of 4. This ln of 5 is going to cancel with the next negative ln of 5. In fact, this negative ln minus 1 is going to cancel the ln of n before it. And eventually, you're going to still be left with, though, this one big number. This is a huge number. And it's a large number. And therefore, because you're going to be left with this large number, this will diverge. Absolutely. Like the absolute version of this, if you take the absolute value, it diverges. And therefore, it does not absolutely converge. So I push this out to you because some of you are saying, well, yeah, fine. You just say that's why it diverges. Yeah, that's a great instinct for you to have and for you able to kind of see how those terms are going to cancel out. There's a reason we did 1C way back on assignment 1. But if you're looking for a specific test that you could do, I did a harder version of that when I did assignment 2, 1I. And when I did that, I compared it, I think, to 1 over n squared. The limit comparison test that you would do for this problem would be to compare it to 1 over n. And you would see that if you compared it to 1 over n, you're going to get a common ratio. Common ratio is the wrong term. You're going to get a non-zero constant for the limit. And therefore, you're going to know that they both converge or diverge together. And because 1 over n diverges, the ln of n plus 1 over n will also diverge. But we have more work to do. Right? We just proved that it doesn't absolutely converge. Now we have to come in and say, does this alternate? Well, yes, it does alternate. And this here, this is a giveaway, right? It alternates. Ooh, what about this next one? I'm not so sure. Is it getting smaller every turn? Is this getting smaller every turn? I don't know. ln of 4/3, then the ln of 5/4, then the ln of 6/5, the ln of 7/6. Is it getting smaller? Well, what are these numbers doing? The ln, the numbers, the argument, right? The thing that we're taking the ln of is getting smaller every turn. It's getting closer and closer to 1. And if we think about the graph of the ln function, I know I'm doing an ultra mini version right here. Here's where it's at 1. And if we're at 7/6, that's closer than 6/5 was, which is closer than 5/4 was. So as we're getting closer and closer and closer, sure enough, it is getting smaller. It's getting closer and closer to 0. So therefore, a of n plus 1 is less than a sub n. And lastly, this equals 0. Why? Because effectively, n plus 1 over n is approaching 1, and the ln of 1 is 0. So this is getting closer and closer to 1, so the ln of 1 is 0. So sure enough, we have conditional convergence. That was fun. So we are done assignment 3 for now. One of the things that I've said to you already is that I said this to you in the notes. Don't do the end of 3 or the last problem on assignment 2 yet, because we're going to talk about errors in our next kind of presentation when we talk about lesson 4. So and then we'll go back and circle back to those problems. Talk to you folks then.